Okay, I'm going to do an Olympiad question with Muirhead's theorem. Let me state the question. Given x, y and z greater than or equal to 0, x squared plus y squared plus z squared equals 1, prove that x squared y z plus x y squared z plus x y z squared less than or equal to 1/3. Okay, well there it is. Let's have a think about this. I can factorise it, of course. X, Y, Z, X plus Y plus Z. Quite often I'll write RTP, required to prove X, Y, Z, X plus Y plus Z less than or equal to 1/3. Well, yes, you can factorise it, but it's not very helpful. That's quite a complicated thing. This restriction here sits poorly with either one of these, really. We've just got to force it into the right form. This is an application of Muirhead's theorem. So what I'm going to do is I'm going to write this plus x y squared z plus x y z squared. It's pretty clearly something like a 2, 1, 1 expression. So let's just write out the definition of that. 2, 1, 1 equals, by definition, 1 over 3 factorial times, and then we've got 3 terms, so we've got 3 factorial equals 6 different terms. X, y, z, x, y, z, oh no, x, z, y, x, y, z, x, oh no, getting it wrong again. These two start with x, these two are going to start with y, x, z, y, z, x, and these are going to be the z. These are all added together. Z, x, y, z, y, x. And I'll just put the powers in 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1. And then we'll notice that these two terms here on the top are the same, because it's x squared y z and this is x squared z y, because the 1's repeated, I guess. So that equals 2 divided by 3 factorial times x squared yz plus x y squared z plus x y z squared. And so this term here, which I'm going to call, for sake of argument, let's call it, I don't know, q. So we know that 2, 1, 1 equals that. So q equals 3 times 2, 1, 1. Now, let's just, what I'm going to do, the overall point is I'm going to take the restriction x squared plus y squared plus z squared equals 1, and I'm going to muck around with this to give terms like 2, 1, 1 or Muirhead type expressions. But however we fool around with this term here, we'll notice that there's a total of powers of 2. The total powers, it's a squared term, whereas this one's fourth, because look, you've got up here, you've got 2, 3, 4. This is fourth order here. So we've got a little bit of a discrepancy. And you'll further remember that Muirhead's inequality says things like this, that says that things like 4, 3, 1 is greater than or equal to, see, these guys total 7 here, so these guys have got to total 7 as well. So that's got to be 3, let's say 3, 3, 1. Okay. Muirhead's inequality has got the total has got to be the same on the left and the right, and we've got 2 here, and in the expression that we were thinking about we've got 4, so we need to take this guy and square it. X squared plus y squared plus z squared. We don't need to square it, but I'm going to. There's other things I could have done as well. I guess I could have multiplied. I could have taken x squared plus y squared plus z squared. I could have done something like multiply it by x, y, z all squared if I'd have wanted to. But you'll notice that because x squared plus y squared plus z squared equals 1, squaring it does two things. It preserves the size of that term, and it's also given us fourth powers here, or something to fourth order. So we're in with a fighting chance, at least, of making it comparable to this term q that we started with here. Well, let's just expand this stupid thing and see where it goes. X squared plus y squared plus z squared, x squared plus y squared plus z squared equals x to the power 4 plus x squared y squared plus x squared z squared plus x squared y squared. I'm doing this term here, but I'm writing them out in alphabetical order, because when I do the expansion, which is not in, well, it's straightforward, but it's a lot easier to do it if you keep track of the terms by always writing everything in alphabetical order. So we've got y squared times x squared, which I'm writing x squared y squared, plus y to the 4, I guess, plus y squared z squared, plus this term now is going to be x squared z squared plus y squared z squared plus z to the 4. Now we're in a position to start mucking around with it in terms of Muirhead's inequality. So I'm going to rewrite it x to the 4 plus y to the 4 plus z to the 4 plus, which are these diagonal terms, I guess. We've got 1, 2, 3, 4, 5, 6 terms left over, and they're in pairs. So it's twice into x squared y squared plus x squared z squared plus y squared z squared. Okay. Well, that's quite nice. This looks to me like a 400 term, and this term here looks like a 220 term, because it's second power 2 power 2 power 2 power 0. I guess there's a sort of implicit 0 in there. And these are both good, because these terms here are comparable to the 211 that we got from the original term. Remember that we got a 211 term, or the quantity was 3 times that, wasn't it? Write that out again more neatly, just a minute. Oops. 3, 2, 1, 1. Sometimes I write commas, sometimes I don't. But the restriction, x squared plus y squared plus z squared equals 1, gives me this thing here. So let me just write out what these terms are. 400 equals, by definition, 1 over 3 factorial times 2 x to the 4 plus 2 y4 plus 2 z to the 4. So that equals 1/3 x to the 4 plus y to the 4 plus z to the 4. It's always as good to write these things out in your head. It's easy to get tangled up here, as I'm doing myself. Therefore, x to the 4 plus y to the 4 plus z to the 4 equals 3,400, which is this term here. There it is. And what about this one? What about this other term here? Is it a 2? No, it's a 1. This one's a 2. This one's a 2. So let's just keep that one there. So we've also got 2x squared y squared plus x squared, x squared z squared plus y squared z squared. And then if I write out 220 explicitly, again that's what, it keeps on doing that and I don't know why, equals 1 over 3 factorial times 2x squared y squared plus 2x squared z squared plus 2y squared z squared. Therefore, 2x squared y squared plus x squared z squared plus y squared z squared, which is the term we want from here. The term we want from, getting a bit tangled up here. The term we want from here equals 6,220. So therefore, x squared plus y squared plus z squared all squared equals the fourth powers, which is this one, 3,400 plus 6,220. And now we know that 3,400 plus 6,220 equals 1, because that was the restriction. This is from x squared plus y squared plus z squared equals 1. And now what we've got to show is that this guy here is less than or equal to a third. So 3, 2, 1, 1, that 3, 2, 1, 1 is less than or equal to 1/3. Well, we know from here, well, we know from here that 3, 4, 0, 0, sorry, I'm just going to divide that one by 3. We know that 4, 0, 0 plus 2, 2, 2, 0 equals 1/3. And we further know from Muirhead's theorem that 2, 1, 1 is less than or equal to 4, 0, 0, and also 2, 1, 1 is less than or equal to 2, 2, 0. Therefore, 3, 2, 1, 1, let's do that again. 3, 2, 1, 1 equals 2, 1, 1 plus 2 times 2, 1, 1, which is less than or equal to 4, 0, 0 plus 2 times 2, 2, 0, which equals a third. Quite a lot going on here. Quite a lot going on here. 3 times 2, 1, 1. All I've done is taken that 2, 1, 1 and I've written 1 copy there and 2 copies there, right? Why am I taking 3 times this? Because that's what we're trying to prove, because we dicked around with it for a long time. Equals 2. Now, this one is true by Muirhead, and this one is also true by Muirhead. Why is it equal to a third? That's because we spent all that time fooling around with the condition to give us that. Okay, so that says that 3, 2, 1, 1 is less than or equal to 1/3, which is what we tried to prove. There's quite a lot going on in that theorem. The hard bit is not Muirhead. The hard bit is taking the terms that you've got and taking, in particular, the inequalities constraint, which is a term of second order. It's got 2 powers of 2 in it, and turning it into something with powers of 4 in it. And of course, what it turned out to be was 2, which way around was it? It was 4, 0, 0, wasn't it? It had, when we multiplied it out, it was a 4, 0, 0 and a 2, 2, 0. Okay? Both of which majorize 2, 1, 1. So we can use Muirhead from there. Without Muirhead's theorem, it's difficult to see how to do this. Well, I spent a little bit of time fooling around with it, and Muirhead is just so neat. It's built for Muirhead's theorem, purely because the original condition, this term here, where was it? The original term right at the beginning, when I phrased it out, when I said it right at the beginning, the original term, which is this one, is tailor-made for Muirhead's theorem. We didn't need to do anything. It was just the restriction that we had to work with. Okay, I'm going to stop there. Muirhead's theorem, wonderful stuff.